welcome to this module. In the last module what we have seen how can we fabricate a piezoresistive sensor on a flexible substrate, and that piezoresistive sensor was made out of a conducting polymer called P.PSS, right. So, if you see the slide, what we have seen is step 1 where we take oxidized silicon substrate, step 2 where we have spin coated PDMS, step 3 where we have form a pattern of chrome and gold, and step 4 where we have formed the piezoresistor. So, these are array of piezoresistors 8 in number. This is a single piezoresistor, SEM image of that. Now, what we will see, how can we form this particular array of gold pads on this piezoresistor. Now, as you know, if I deposit metal on semiconductor, it will get short, right. So, that is why we have to have insulating material. So, if I see the process flow, how it will look like, I have a substrate which we have seen in the last module, which has PDMS, and on that PDMS interdigitated electrodes on which there are piezoresistive sensors P.PSS. These are my, let us say, interdigitated electrodes, or you can not interdigitated electrodes, these are actually patterns or contact pads, because it is like this, right, it is like this, and then on this I have piezoresistor like this, alright. So, it is a chrome gold pattern, I will say. So, I will say chrome gold, this one would be PDMS, and this is silicon. On this substrate, what we want? We want to have a contact pad which will sit over here, alright, which is gold contact pad. But if I deposit gold directly on this, then it will get short. That is why the next step would be, I will deposit insulating material, and this insulating material, the pattern would be this X or cross, okay. This is my insulating material. So, if I have this one, then what I will do is, I will spin coat photoresist, and this time I will spin coat negative photoresist, okay. Then I will load the mask. So, after spin coating negative photoresist, next step would be soft bake, right. After soft bake, so this one would be negative photoresist, then I have a mask which is my bright field mask, and it will only open the contact area. This is my bright field mask, my photoresist is negative photoresist, okay. Photoresist is negative photoresist, bright field mask. After that, as you know, we would expose the wafer with UV light. When you expose the wafer with UV light, since you have used negative photoresist, the unexposed region would be weaker and the exposed region would be stronger. So, what we will have? We will have a wafer with PDMS and interdigitated electrodes over which there is a piezoresistive sensor on which there is a insulating material, which is my silicon dioxide. This silicon dioxide we can grow with help of PECVD, alright. This silicon dioxide PECVD, PECVD stands for plasma enhanced chemical vapor deposition, and then I will have my photoresist like this. This is my negative photoresist. All right. As you see here, the photoresist from this two area got etched, is not it? So, when the photoresist gets etched, then I can remove my silicon dioxide below it, right. And why the negative photoresist got etched from this area? Because we have used bright field mask and the unexposed region for negative photoresist will become weaker, right. For positive photoresist, the unexposed region, say unexposed region. If I talk about positive photoresist and negative photoresist, the unexposed region in positive photoresist would become stronger, and the unexposed region in the positive photoresist, unexposed region in the negative photoresist will become weaker. What we have used? We have used negative photoresist. So, the unexposed region is weaker. Next step would be, I will dip this way, I will perform hard bake, and after hard bake I will dip this wafer in silicon dioxide etchant. What is my silicon dioxide etchant? Silicon dioxide etchant is buffer hydrofluoric acid or BHF. When I dip this wafer in BHF, what will I have? I will have this pattern, okay, because the silicon dioxide will get etched. This X pattern is for silicon dioxide, right. This is my chrome gold, this is silicon, and this one is PDMS. You can have oxidized silicon, all right. Next step is that I have to deposit chrome gold on silicon dioxide, but before that we have to remove the photoresist, or we have to strip off the photoresist. So, after this, next step would be, so when you expose the wafer and you develop the photoresist, you have to perform hard bake. Okay. After hard bake, you have to dip the wafer in silicon dioxide etchant. When silicon dioxide gets etched, the next step would be, we will dip this wafer in acetone. When you dip this wafer in acetone, what will happen? You will have your photoresist stripped off from the wafer. Next step is that you deposit chrome gold, again you deposit metal, chrome gold, right. And since chrome gold is shown by dot pattern, we will use same pattern, okay. Now, next step would be, I will spin coat this one. So, let me remove this particular or let me make it short, so it becomes easy, okay. So, next step would be, after I have deposited chrome gold using my PVD method, physical vapor deposition, the next step is, I will spin coat positive photoresist, all right, spin coat positive photoresist, then perform soft bake, then I will load a mask, and the mask will be such that it will have a pattern like this and like this and this. So, what is having? I am saving my gold from the contact pads, which you can see here in the pattern, which is my mask. Okay, this is my mask. This is my mask, and I am saving the, or not allowing the photoresist to get exposed from this region, since I want to protect my gold below this region, and this region will form the gold pad, So, after this I will expose the wafer with UV light, then perform photoresist developer. Now, what then perform photoresist developing. So, photoresist photoresist will get developed from the area which is exposed, and the unexposed region would be stronger. Why? Because this time we have used the positive photoresist, correct. So, what we will have? We will now have a photoresist which will be protected in this region, on this region and this region. This is my positive photoresist, correct. Next step is I will dip this wafer in gold etchant, then rinse it, then I will dip. So, after this of course, there is a hard bake 120 degree 1 minute hot plate, followed by dipping the wafer in gold etchant, then rinsing the wafer, then dipping the wafer in chrome etchant, rinsing the wafer, and when you do that, what you will have? You will have this pattern where the chrome gold got etched, which in the area which was not protected by the photoresist, right. This is chrome gold. Next step is I will dip this wafer in acetone. When I dip this wafer in acetone, what will happen? The photoresist will be stripped off. When photoresist gets stripped off, my wafer that I have patterned it like this will look similar to my pattern number 6 and this particular platform, right. So, what we have done? We had a substrate with PDMS and P dot PSS as strain gauge, on which we have insulating material, which is step number 5, right, and then we have performed a photolithography and remove the contact, then we have deposited chrome gold and we have patterned to form the gold pads. What is the next step? Next step is to form SU8 pillars. Next step is to form SU8 pillars. So, on this what will I do? I will now spin coat, right. I will now rather than spin coat, we will grow now. Okay, for our step is to have SU8, right, SU8. So, what we will do? We will spin coat, we will spin coat SU8, because SU8 is a polymer, right, and it will act as negative photoresist. So, I will spin coat SU8 onto this particular substrate, which substrate? This substrate, this one, all right. So, when I spin coat SU8 on this substrate, SU8 is a negative photoresist. What I want? That there should be SU8 pillar on each of this gold pad, like you can see here, right. I want to protect SU8 on the gold pad. SU8 is a pillar, all right. I will tell you why we are making these pillars, okay. I will tell you. So, when we coat SU8 using spin coater, the next step would be to protect SU8 only in the center. So, I will load, I will of course perform the soft bake in SU8, you know. Again I am telling here, please pay attention, photoresist positive and negative, SU8, SU8 acts as a negative photoresist. What is the difference? With spin coat, this also spin coat. Next step, soft bake 90 degree 1 minute hot plate, soft bake, this is done at 65 degree. For time on hot plate, this time depends on the thickness of SU8, all right. Then there is a UV exposure, then developer, and then hard bake. Hard bake is done at 120 degree centigrade on hot plate for 1 minute, right. In this case, 65 degree soft bake, then UV exposure, then hard bake, again temperature is 95 degree centigrade, time depends on the thickness of SU8 on hot plate. Then we will form developing. You see this is the difference, UV soft bake, UV exposure, developer and then hard bake. Here soft bake, UV exposure, hard bake and developer, that is the difference. Okay. So, that you have to remember when we talk about SU8. So, SU8X is a negative photoresist, that means the unexposed region will be weaker and the exposed region would be stronger. Exposed to what? Exposed to UV light, right, exposed to UV light. So, now we will have a mask, we know that SU8X is negative photoresist and we want to protect SU8 in the center. So, what we will do? We will use a bright field mask, and by using bright field mask what we are doing? We are protecting the layer of SU8 which we do not want to get developed in the SU8 developer. Okay. So, how does it happens? Because SU8 is negative photoresist. If SU8 is negative photoresist, then the area which is not exposed, right, will be weaker, correct. Area which is not exposed will be weaker. So, if I use this mask, will it work? It will not work, because we are removing SU8 from this side, which is not what we want. We want pillars here. So, our mask should be having pattern like this. Correct. The area which is not exposed will be weaker, because SU8 works similar to negative photoresist. Now, if I use this mask and if I expose the photoresist to UV light, what will happen? If I develop this wafer, I will have silicon wafer, PDMS, interdigitated electrodes, strain gauge, right. Then insulating layer, right. Insulating layer is our SiO2, and this is also our metal contact pad. Now, when I say interdigitated electrodes, it does not mean like it is interdigitated, it is actually the contact electrodes. Let us say it is a contact electrodes, all right. On this what you have is you have gold pad here, right. So, you have gold pad here, and on this now you have SU8 which is exposed with a UV light, and this is the mask. So, if we use this pattern, then we will have SU8 on the gold pad. So, SU8 will stay here, this is my gold pad, these are contact pads, then silicon dioxide, contact pads again, this one would be PDMS, this is my silicon. So, what we have here is the one which is similar to this one. Okay. But And what is the role of this? What is the role of this SU8 pillar? Now you understand that if I apply a force, to this area, right, then SU8 pillar will act as a force transducing mechanism. So, the force will be applied to the strain gauge through SU8. Another point is, I want this SU8 pillar to be conductive. Why? Because you see here, if I have gold pad below it, right, and if the SU8 pillar becomes conductive, if it becomes conductive, then this together SU8 pillar and gold pad will act as electrode 1. I will tell you what is the role of electrode 1. Okay. If the SU8 is conductive, SU8 along with gold pad will become electrode 1. Alright. Second role of SU8 is when I apply a force, then this force will reach to the strain gauge, which is my piezo resistor, right, which is this one, piezo resistor P dot PSS, through SU8 pillar, okay. Now, how it will bend, we will see how this will bend and how when you apply force, because this silicon substrate here, right. So, if I apply force, silicon will not bend, and that is why I do not want silicon. So, I will remove silicon at some point of time, but until here I hope that all of you understood, right. Next step, what is the next step? Now, we have to make SU8 conductive, and for that, if you remember, I have taught you a process called lift off technique, right. So, let us use our lift off technique and coat this SU8 with a metal, so that SU8 and the gold pad below SU8 will become electrode 1. Okay. So, let us see here in the slide. So, you have this particular thing, right. So, I will draw it here again, it becomes easier and we will start from there. So, again I am repeating, please focus here. You have silicon substrate, you have PDMS on silicon substrate, alright. This is your PDMS, this one is your silicon, then we have contact pads or contact electrodes, then we have here P dot PSS strain gauge, right. Then we have insulating material, which is my silicon dioxide, alright. So, this one is silicon dioxide, this one is P dot PSS, this one would be contact pads, right, and then I have here gold pad on which I have SU8 pillar. This is SU8, this is gold, alright. Now, what I want? I want SU8 to be conductive. So, we will use lift off technique, coat the SU8 material, and in lift off technique what we will do? We will coat everything with photoresist, and this will be our positive photoresist. Okay. So, let me use this design for positive photoresist, okay, and this is positive photoresist. Now, after this we will open a window only in this region, and this region we will save the photoresist. Okay. So, what we will do? We will use, after positive photoresist we will perform soft bake. After soft bake we will load the mask and load mask such that we will protect the positive photoresist in this area, and the center area which is having SU8 we will not protect photoresist. So, this photoresist you see the area is little bit bigger than the SU8 area. Okay. The opening, the window opening is slightly wider than the SU8 area. Okay. This is your mask. Which kind of mask? Bright field mask. Alright. Next step, you know, you have to expose the wafer with UV light, UV light, right. After that, you have to develop the wafer, you have to unload the mask, develop the wafer. When you develop the wafer, what will happen? Since there is a positive photoresist, the area which is not exposed will become stronger. The area which is not exposed will become stronger, the area which is exposed will become weaker. Now you can see that we have positive photoresist, right, and here we have opened the window. This is a window that we have opened, correct. Now what we will do, you know, we will deposit gold or a metal everywhere, chrome gold, right, as usual, chrome gold everywhere. And then the next step is we will dip this wafer in acetone. If I dip this wafer in acetone, what will happen? Acetone will strip off the photoresist, right, because it is a positive photoresist stripper. When it strips off the photoresist, it will lift off the metal above it, and the metal where it is directly deposited on SU8 pillar will remain intact. That means that when I dip this wafer in acetone, what will happen? My photoresist will get etched from everywhere like this, and I will have my metal coated on the SU8 pillar. My metal will get coat on SU8 pillar. Now you see, you have a gold pad, right, at the bottom. Over that there you had SU8, and now SU8 is coated with metal. That means SU8 and gold pad together will become electrode 1. You got it? So now what we have? We have a strain gauge made up of P dot PSS, we have a electrode which is made up of gold pad and SU8 which is coated with metal, thus SU8 becomes conductive, and next step would would be to strip off the PDMS. So if I strip off the PDMS from the silicon substrate, what will happen? This will happen. So now what I have? I have a flexible sensor on which there is P dot PSS integrated piezoresistive materials or piezoresistive sensors, and I have electrode 1 which is formed with the help of SU8 which is conducting on gold pad, and the strain gauge which is made up of P dot PSS is separated by an insulating material which is silicon dioxide from the electrodes. So, electrode and P dot PSS is separated by silicon dioxide in between. So, there is no shorting, alright. When you perform this, then you see we have after 6 we have now coated the we have spin coated SU8 and pattern SU8 pillars. Then with lift off technique we have coated gold, right, which is 8, and finally we have stripped off the PDMS from silicon substrate. So, it will become a flexible sensor as shown in this schematic, alright. In the sensor photos, if you see, this is a flexible sensor here as well as here, alright. If you see this particular photo, then you will understand that there are 3 contact pairs. Why 3 contact pairs? 2 contact here, 1 and 2 contact for this, and 1 contact for your SU8 pillar, like this line, right. So, 1 contact for this. Another thing you will observe, so this is 1, 2 and 3, right. That is why if you see here, this is 1, this is 2 and this is 3, 1, 2 and 3. Another thing that you need to observe is that the lines are not straight, these are wavy lines like this, you see the wavy lines, is not it. Why it is wavy line, why not straight? Because if I have straight line, if I flex the, since the material is flexible, there would be lot of stress in the film and film will get cracked. To avoid crack, we have designed the contact pads and the connecting lines in this particular fashion. So, all the things that we have discussing, it is right in the center of this particular sensor, all right. So, we have 8 piezoresistors and we have 8 electrodes, right. Electrodes means SU8 which is conducting over gold pad, this is our one electrode. Same way there are 8 electrodes as you can see in this particular figure, right. So, the center like what we were saying, right, has all the sensors, right, including your 8 piezoresistor and your 8 electrodes, alright. Now, let us see how can we use this flexible sensor for understanding the or you can in another terms, technical term is phenotyping tissue properties. Phenotyping, we will do 2 types of phenotyping, one is the electrical understanding, electrical signals and the mechanical properties. So, let us see how can we use this. Now, you see here this electrode that we have fabricated, right, this flexible one which is this one is connected. So, there are 8 of those, right, like this 8 of those, right, that this is the sensor. This is connected to a cone, you see here to a cone. So, the tip is on this side, all this 8 that you see SU8 pillars would be on the bottom side, right, and there is a cone like this, right, and a sensor is connected. These are all the connecting wires that you can see on this particular figure, right. And now, this is pressing something, right, and what is the something? Something is there are contact pads on the glass, contact pads on the glass. What does it mean? You have this structure on the glass, alright. What is this? This is a mesh structure, MESH. So, if you see this one, these are microgrid or mesh for holding tissue core. So, if I load tissue on this, right, if I load tissue on this like this is the figure, correct. How to create this? Simple, it is a one step photolithography technique, right. How to create this? This is on the glass slide, okay, like this on the glass slide there is a mesh. How can we create this? Simple, you see, you take a glass slide, glass, then on that you coat metal which is your chrome gold, then you spin coat photoresist, positive photoresist, then you use mask, bright field mask, something like I am just showing a representative diagrams, right, bright field mask, then you expose the wafer with UV light, you expose the wafer. After exposing wafer, you develop this glass wafer. When you develop the glass wafer, what you will have? You will have your chrome gold and your photoresist protected in the area which was not exposed, since it is a positive photoresist, right. Then you dip this wafer in chrome etchant followed by DI rinse, then gold etchant followed by DI rinse, right. When you do that, what will happen? When you perform that particular process, then you have chrome gold etched from the area which was not protected by positive photoresist right, and the area which was protected by the photoresist will be saved or protected. Next step, you know, right. So, after developing, of course, there is a hard bake, then you have to do chrome gold, you have to remember the photolithography steps. Okay. Now, if I dip this wafer in acetone, what will happen? If I dip this wafer in acetone, then photoresist will strip off and I will get the pattern, and this pattern is this pattern. Okay. This much is easy. Now, you understand that when I am pressing my, there is a cone, right, which is connected to a micro manipulator, as you can see here, and on this cone there are 8 pillars, right, 8 pillars are there. So, if I select a different color like this, there are 8 pillars pressing this tissue, all right, and this is the breast tissue core on micrograde. What will happen when I press this tissue with the help of the micro manipulator? You see here MP285 micro manipulator. So, this cone is connected to a glass slide, this glass slide is connected to the micro manipulator 285 MP 285. Okay. So, when you indent it, what will happen? When you indent it, depending on the elasticity of the tissue, the sensor will bend, and this bending of sensor is this sensor, right. So, it is a flexible sensor. So, if I just use one rectangle to represent sensor, when I apply a force, the rectangle will bend like this, since it is a PDMS material, right. This is a PDMS material. So, when it bends on applying of force, what will happen? There is a change in resistance because of the piezo resistor, which is your P dot PSS, right. And now, if I apply a voltage, this is a conducting material, right. This will be your electrode 2. Electrode 1 you already know, this is your electrode 1, correct. Electrode 1 is your SU8 material with your AU pad, and electrode 2 will be the bottom electrode on which you are loading the tissue. Now, when I apply a voltage between electrode 2, which is the bottom electrode, and electrode 1, which is your SU8 pillars with your gold pad, what will happen? Depending on the resistance of the tissue, the current will change, right. So, if I apply voltage between electrode 1 and electrode 2, the current will flow depending on the resistance of the tissue. So, now we can measure the elasticity by pressing the tissue, and we can also measure the resistance of the tissue. This is the advantage of simultaneous measurement of electromechanical properties of tissue, and you can see here in this data that for a normal and for the IDC, which is invasive ductal carcinoma, the elasticity for the normal is higher compared to invasive ductal carcinoma, and the resistance of the normal is lower compared to invasive ductal carcinoma. We can also learn about epithelial and stromal regions, same way for IDC and normal. Here you can see there is an inverted microscope, and inverted microscope is used so that you can see the tissue when displaced on the microgrid. Okay. So, this is the last slide of this particular module. In the next class, we will see how can we design one chip which can also, it can not only do electrical and mechanical, but also can also perform the thermal properties, thermal characteristics, or also sense the thermal characteristics. That means that it will measure the stiffness or elasticity, it will measure resistance, and it will measure the thermal conductivity, all three things. Here it is electrical and mechanical, there will be electrical, mechanical and thermal, and we will see, and that we will design on the silicon chip. Again, for understanding three properties of tissue, which is electrical, mechanical and thermal, we will use a few videos to explain you what is breast cancer, and what are the types of breast cancer, and how it is different. Same way when you talk about prostate cancer, it is also different, right. Same way when you talk about the brain tissue is different, liver tissue is different, stomach tissue is different. Can we use electrical, mechanical and thermal modalities in addition to the existing biomarkers for better diagnosis of a disease? That is our idea. This is a biosensor, or you can say sensors, right. Alright. So, I will see you next class with more interesting fabrication of a biochip which can do three properties simultaneously. Till then, you take care. Bye.